Let's talk about the buoyant force. Now, we've talked in another video about if I have a fluid here, then the deeper I go, the greater the pressure is coming from the fluid. Which means if I have an object here, I have pressure because of that amount of depth, and then I would also have pressure from that amount of depth, and the deeper I am, the greater the pressure. And so there's a pressure difference between these two levels. Since I have more pressure below than I do above, that means I'm going to have ultimately a force acting up here, and I'll have a force acting down here, but the force acting up is bigger than the force acting down. So there's a net force upwards that is known as the buoyant force, which I'm using F sub B. So we started out with F town or F tong, depending upon which group is watching this. And then we added a spring into it, so we tacked on an S onto the end, so F tongs. And then we are now adding another force, the buoyant force, so Facebook town or Facebook tongs. So let's go through the derivation here. So I've got the top, I'm using T for top and B for bottom. So the top is at a certain depth, the bottom's at a lower depth, as mentioned before. Therefore, the force from the bottom on the object, so the force on the bottom from the object and the force from the top on the object are unequal. The force is equal to pressure on top times the area, surface area up here, and pressure on the bottom times the surface area down here. And I know that pressure is equal to the density of the fluid times the acceleration due to gravity times the depth. Now in the previous video I used H, but I'm using D right now because I've defined D that way. And so that actually should be an O right there and O right there. Depth to top of object, depth to bottom of object. So the difference in the force, so I know that the bottom force is greater than top force, so I'm going to do bottom minus top. End up, well, also I'm letting up be positive, so that's a positive force, that's a negative force. And so then it is this is the pressure. I have this pressure acting on the bottom of the object times the area of the object minus the pressure acting on the top of the object times the area of the top of the object. And so I've got some common factors here. I have the density of the fluid, I have the acceleration due to gravity, and I have the area. I am assuming some symmetry here, that the top area and the bottom area are the same. And if it's an irregular shaped object, it just requires more sophisticated math, but you still come out to the same answer. And so if I factor those out, what I basically am left with is that the density of the fluid times acceleration due to gravity times the area, surface area of the top and bottom of the object times the depth of the bottom minus the depth of the top. Well, that depth of bottom minus depth of top is just this distance right here. Basically a height. So I have a height of an object times the area of the object. That's the volume of the object. And so the buoyant force is equal to rho FGV. This is the volume of the object. So what's happening here is that the buoyant force is equal to, well, that is just the weight of the water that has been pushed out of the way because that object's there. Because density times volume is equal to mass, and so we basically have an mg. So this is the mass of the water that has been pushed out of the way to make place for that volume, which is what I have written right there. So let's take a think about that cube. We're at 0.5 by 0.5 by 0.5 cubes submerged in water, and the buoyant force would be the density of the water times the acceleration due to gravity, assuming it takes place on Earth, times the volume of the cube, which for a cube is just one side cubed. Multiply it out, and you end up with that amount of force acting up on it. Now recognize I do have two things going on here. I have that buoyant force. That doesn't mean the object's going to float because I have over 1,000 newtons there. That's 200 and something pounds. The weight is still acting down, and so I still am competing. And I didn't give you enough information to know what the weight is, whether this object would float or not. If I think about another example, what is the buoyant force on me from air at 20 degrees Celsius, which is room temperature-ish? Density of the fluid, this is the density of air at 20 degrees Celsius. This is the acceleration due to gravity, close enough. And my volume, as found in another video based upon density, my volume, and I end up with this is the amount of force that's acting up on me because I'm in air. Now my weight is somewhere around 980 newtons, and so this is a very small bit, but it does mean that the scale is just a little bit off of what my actual weight is. So now if we think about an object sitting on a balance, I put an object on a balance and I find its mass m. I submerge it in water and find its mass m sub naught. And you can do this physically. If I have a balance here, and this is my symbol for a balance, I put a mass on it. This is a triple beam balance. Sure, we'll make it a triple beam balance. You find the mass, and then we can find it submerged in water by taking that triple beam balance and dangling the mass from the bottom of it into water or whatever fluid you happen to be using. But we found the mass of it. And so I have a difference in, there should be a different value between the mass I'm measuring with it sitting on the balance and the mass I measure with it dangling below. When it's in the water, I have the weight acting down, which is that mass times acceleration due to gravity, and then I have a buoyant force acting up. That difference there should be the mass of the submerged object, m sub s. So m sub s g should be the actual weight minus the buoyant force. Doing the fancy math here, bringing this over to the other side, I get msg minus mg is equal to the negative of my buoyant force. I'm going to flip sides there so that I'm dealing with just the first term being positive. It's a me thing. And then I factor out g, so I have m minus msg. If I divide by the acceleration due to gravity, g cancels out. And what I'm left with is the density of the fluid times the volume of the object is equal to the difference in the mass measured on top of the balance and in the water. And then if I solve for the volume of the object, it's just the difference in the masses that were measured divided by the density of the fluid. If my mass is in grams, I know that the density of water is about 1 gram per cubic centimeter. Therefore, if I'm looking to find the volume of an object, I can, because rho is now 1, and we end up with the volume in cubic centimeters. So this is in cubic centimeters. Would just be the difference in the mass measured here and the mass measured there. And that should be incredibly helpful for one of the labs, whether you do it this semester or not. There's a standard lab on Archimedes' principle.